Hi everyone! Today we're going to learn about 3.10 related rates. So actually there are three important application topics in Calculus 1. Related rates and the optimization problems. So these two topics are the hardest topics in Calculus 1. So I really hope today when you read the video, please read it carefully. Listen carefully. Make sure you understand each step. Okay, so maybe at some step if you don't understand, please pause and think about more, or maybe you can print screen and ask me questions. Okay, so this class is very, very important and challenging. So please listen carefully. Cheers! Okay. So, big idea. Oftentimes, one quantity depends upon two or more quantities that are all changing with time. To find the overall rate of change, you need to use the chain rule to relate all the rates of change. Okay? Big skills. You should be able to write a function that describes a real-world situation and then relates its rate of change to the rate of change of other quantities. Okay, so here are the procedures or steps. Okay, first steps, we want to draw the picture and name the variables. So how do we name the variables? We read the problem and think about what is changing. If it's changing, usually for horizontal distance, we call it X. For vertical distance, we call it Y. For area, we call it A. And for volume, we call it V. Okay? And what is constant? Give it the number. If it's a constant, you don't need to name a variable. Variable only varies, right? So if it's a constant, just give it the number. Don't name a variable for it. That is the first step. And then second step, we write the relations. Okay, and all the formulas relate those variables. Okay, and then the third step is implicit differentiation. So we differentiate both sides with respect to time t. Okay, so step 4, after we differentiate, we substitute the known values and solve for the desired quantity. Okay, usually we are asking find the rate of change of some quantity, and then we plug in the values and solve for that as step 4. Step 5, check that the units are consistent and the answer is reasonable. For example, you don't expect the volume or length be a negative numbers, right? It wouldn't make sense if the area is negative. So check your answer. Okay? Alright, so before we work on an example, I would like to review all the geometry shape. Okay, we have 2D and 3D. So for 2D figures, we have the basic one, square. Square, what is area? Area is S times S square, right? And then the perimeter is, we have 4 sides. Each one is S. So that's why the perimeter is 4S. And then next one, we have rectangle. The area is length times width. The perimeter is, we have 2 length plus 2 width. Okay? For triangles, the area is 1/2 base times height. So actually, how do we get this formula? Let's look at the parallelogram first. Okay, so here is a parallelogram. Okay? You can see if I cut this piece and tape it here, I actually get a rectangle. Now my length is the base A, and my width is what? Is the height H. So that's why the area of the parallelogram is base times height. Oops. I think here there's something wrong. The base is actually B. Okay, base times height. And the perimeter is 2A plus 2B. Okay, or maybe let me change this guy to BA. Okay, alright. Okay, so that's why we come back to our triangle. You can see when we have 2 copies of the triangle, we actually get parallelogram. And the area of parallelogram is base times height. So that's why the triangle is half of the area of the parallelogram, which is base times height. Okay, and the perimeter is A plus B plus C, right? The sum of the three sides. Okay, how about trapezoid? How do we find the area of a trapezoid? So here, if we consider two copies of the trapezoid. Oops. Okay. I think I pressed something wrong. Okay. Alright. So let's do it. Okay, if we have two copies, then this is B. Right. You can see here, after we get two copies of the trapezoid, we actually get a parallelogram. And what is the area parallelogram? Base times height. So the new base is actually capital B plus small b. Okay? And so the trapezoid is half of the parallelogram, and then the area parallelogram is capital B plus small b times h. And the perimeter is you add those four sides up, right? Okay, and then we have circle. We know the area of the circle is pi r squared, and the circumference of the circle is 2 pi r, which is also pi times d. D is the diameter, r is the radius. Okay, so those are the two-dimensional. Okay, how about three-dimensional? The easiest one, the cube. Okay, the volume is S cube, right? Surface area, how many sides? How many sides on a dice? Yeah, 6 sides, right? So that's why the area, the surface area, we have 6 sides, and each of them is S squared. So that's why we have 6S squared. Okay, for rectangular solids, the volume is length times width times height. It's actually area base times height. So for all the cylinders, so we can consider the rectangular solid is a type of cylinder where the base is a rectangle. And then we have the right circular cylinder is a type of cylinder where the base is a circle, right? So for all the cylinder, the volume is always area of base times height. Okay, and the surface area here, we have 6 sides. The back and the front is 2L times H. The left and right is 2 width times H, and the top and the bottom is 2L times width. So that's why we have the surface area as this formula. Okay, and then for the right circular cylinder, volume is area of base times height, but the area of the base is a circle, pi r squared times height. And then what is the surface area? Well, when we cut it, we have the top and the bottom, they are a circle, so that's why it's 2 pi r squared. And for the sides, when we cut it and open it up, this is actually h. And then the length is actually the circumference of the circle, so that is 2 pi r. So that's why the area of the side is 2 pi r h. The surface area is 2 pi r squared plus 2 pi r h. Okay, for cone, the volume of cone is 1/3 times pi r squared h. Last one, sphere. The volume of sphere is 4/3 pi r cubed. The surface area of the sphere is 4 pi r squared. Okay? Alright. Next, let's start to work on example 1. Okay? 2 small planes approach an airport. One flying due west at 120 miles per hour, and the other flying due north at 150 miles per hour. assuming they fly at the same constant elevation. How fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport? So let's draw some picture. Okay, one flying to due west, so we're flying here, and I think my plane looks like a flying fish. It's okay. The other one flying due north at 150. Okay, so let's say this is the airport. Okay, a plane flying due west, the other plane is flying due north. Okay, and let's see. Here, another flying fish. Okay, so this guy, the speed is 120 miles per hour. This guy, the speed is 150 miles per hour. Okay? How fast is distance between the planes changing? So we're actually asking the rate of change of the distance between the planes. So let's set the variable. Okay? When the plane is flying, we can see this guy change. So let's call it X because it's like a horizontal distance. This guy is also changed. They decrease, right? The distance decreases. And then we call Y. So the distance between the two planes, let's call it Z. Z is also decreasing. Okay? And what are we looking for? Our goal is to find the rate of change of the distance between the planes. Okay, when at the moment when the westbound plane is 180 miles, so that is X. X is 180 miles and the Y is 225 miles. Okay, so that is the first step. We draw the picture and then we figure out, okay, what are the variables, what are the constants, what are the informations in the problem. Okay, that is the first step. The second step, we want to kind of find what is the formula and relationship between the variables. So here we have a right angle triangle. And then we have the variable, the other sides of a right angle triangle. What formula can you think of? Yes, Pythagorean theorems. So we have x squared plus y squared equals 2z squared. Okay, so that is the formula. Okay, that's step 2. Step 3, we want to differentiate, implicit differentiation with respect to time. So the derivative of 2x is 2x. So be careful in session 3.7. When we do the implicit differentiation, we differentiate with respect to x. So when we when we take the derivative of x, dx is like 1. When we differentiate y, we multiply by y prime at the end. But here, because we're taking the derivative with respect to time, so for all the variables, no matter x or y or z or a or v, after we finish, we are using chain rule. So we have to multiply by d of the variable over dt. Okay, so 2x. After we finish differentiating that, multiply by dx dt. And then here is 2y times dy dt. The derivative of 2z is, the derivative of z squared is 2z dz dt. Okay? Yes. And then, alright, now let's see. Can we simplify? Can you see both sides? We have the 2. So let's divide it by 2 on both sides. Then we have x dx dt plus y dy dt equals to z dz dt. Okay, now let's see we can whether we can plug in the values. So x is 180. What is dx dt? Well, dx dt is the rate of change of x. So that is actually 120. Oops, my equal sign doesn't look good. Okay. Yeah, and furthermore, because the distance x is decreasing, so the dx/dt should be negative 120. So this is negative 120. The y is 225. How about dy dt? Well, the distance y is actually decreasing, so the y dy dt is negative 150. And then what is z? Okay, so we are looking for dz dt. Okay, so what is this z? Okay, so think about, now we're looking for the z at the moment when the x is 180 and the y is 225. What is your z? By the Pythagorean theorem, is 180 squared plus 225 squared. Okay, now let's see dz dt equals to, so the left hand side, 180 times negative 120 plus 225 times minus 150 all over z. Z is square root. Oops, my square roots. Let's make it look better. 180 squared plus 225 squared. Okay, so plot this in your calculator. What do you get? Let me grab my calculator and let me calculate these numbers. Okay, let's pause here. Alright, so the answer I get is minus 192.09. Do you get the same thing? So what is the unit? Yes, rate of change, mile per hour. Okay? Alright, that is example 1. Let's see. The first step, we draw the picture, we name the variables, and then we figure out what we're looking for. Step 2, we find the relationship between the variables, right? And then step 3, we do implicit differentiation and we take the derivative with respect to time. So for all the variables, we have to multiply by d of the variable over dt at the end after we differentiate the variable. Okay, and then step 4, we plug in the values and then we solve for dz dt. And then step 5, let's check our answer. You see the answer is negative, so it means the distance is decreasing, right? If the rate of change is negative, so the distance between the planes is decreasing, and that makes sense, right? Okay, so that is example 1. So make sure you understand each step. If you don't, it's okay. Print screen and then ask me. Okay, I'm very happy to explain to you. Okay, all right. Let's go to example 2. Sand falls from an overhead bin, accumulating in a conical pile, with a radius that is always 3 times its height. If the sand falls from the bin at the rate of 120 cubic feet per minute, how fast is the height of the sand pile changing when the pile is 10 feet high? Okay, so we have the sand right here is falling, and then it form a conical pile. Okay. All right. So a cone. What do we care? Oops. We care about the radius and the height, right? And then at this sentence, we know the radius is always 3 times its height. So now it already tells us one relationship between the variables r and h. Okay, if the sand falls from the bin at a rate of 120 cubic feet per minute. So what is that? We can see from the units. Okay, so per minute means this is a rate. Okay, this is a rate of what? Cubic feet. You know, if we see feet, that is length, right? If we see square feet, that is the area. When we see cubic feet, what is that? Yes, that is volume. Did we press something? Okay, let's come back. All right. Okay, so where are we? Okay, and because the sand, we're getting more and more sand, so that's why the rate of change is a positive number. Okay, and then we're asking how fast. So our goal, what is our goal? How fast is the height of the sand pile changing? So we're asking the rate of change of the height of the sand pile when at the moment the sand pile, the pile is 10 feet high. Okay, so that is step 1. We draw the picture and we figure out the information. Step 2, let's write down the relationships. Okay, so we have one relations r equals to 3h. The other one, because here we are looking for dh dt and we have dv dt. So we want to relate the volume and height. What is the volume? For cone, the volume is 1/3 pi r squared h. That's why I review all the area, volume of the 2-dimensional and 3-dimensional geometry with you. Okay, so and that is why students find this sessions related rates very challenging, because different problem, different story, there is a different picture and different formula involved. So you have to be careful, and you're gonna need a lot of so be prepared. All the geometry formulas, all the common formulas like the Pythagorean theorems, those stuff. Yeah. Okay. Next. You can see here, we kind of relate V and H, but there's R there. Okay, we want to get rid of the R because we want to relate V and H, right? So what is R? R is 3h. Okay, so what is that? So this is 1/3 pi. 3h squared is 9h squared h. And then 9 and 3 cancel. We have 3 pi h cube. Right? Yes. So this is the relation between V and H. And we are ready. Okay, let's differentiate both sides with respect to t. So the left hand side we have dv dt. The right hand side 3 pi constant multiple stays here. Derivative of h cube is 3h squared dh dt. Okay. And we're ready to plug in numbers. Okay. Oh, another typical mistake is students plug in the values here instead of after we differentiate. We always plug in the values after we differentiate. Think about it. If you plug in the values here, you don't see the rate. You're looking for the rate of change dh dt. You don't see the rates here. Even though you plug in the number here, you're not able to find the rates, because there's no dh dt there. So we must plug in, substitute the values after we differentiate. Okay? So here dv dt is 120. And then here 3 and 3, that's 9 pi h. So we're looking for dh dt at the moment when h is 10. So h squared is 100. And then we have dh dt. Okay, so let's solve for dh dt. That is 120 over 9 pi and 100. 0 cancel. And then I can cancel the 3. And then I can cancel the 2. Okay, so the answer is 2 over 15 pi. And what is that? Okay, let me plug this in my calculator. So the answer is 0.04244. Okay, so 0.04244. And what is the unit? So it's height, so feet per minute. Okay, so do you get the same answer? Okay, great. Let's go to the next problem. Example 3. An observer stands 200 meters from the launch site of a hot air balloon. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after the launch? Okay, let's draw a picture. Alright, so we have so we have a hot air balloon. Does it look like a hot air balloon? Maybe something like that, right? Let me draw a bit better one. So it's like that. Okay. Alright, so we have a hot air balloon and it's rising up, okay? And observer, we're here. We're standing 200 meters from the launch site of a hot air balloon. The balloon rises vertically. So the balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation? So angle of elevation is the angle between the ground and the observer's line of sight to the balloon. So this is the line of sight. So this theta is the angle of elevation. Okay, so let's click theta, and here you can see the balloon is rising. So let's call this vertical distance y. Let me ask you, how about the horizontal distance? Do we call it x? Does that change? No, it's always 200 meters. The observer is not moving at all. So this is fixed. If it's fixed, we just give it the number. Don't name the variables. If sometimes you name too many variables, then you realize, okay, when you differentiate, there's not enough information to plug in. And yes. Okay, so this is our picture. And what we're looking for? How fast is the angle of elevation of the balloon increasing? Okay, angle. So we're looking for the rate of change of the angle. Okay, increasing after 30 seconds. Okay, so this is our goal. So we want to relate the angle of theta and y and the 200 meters. Let's see, do you remember? This is a right angle triangle, right? What is the opposite over adjacent? Which trig function is that? Yes, tangent. So tangent theta is y over 200. Right? So this is the relation between theta and y. Okay, so now let's take the derivative with respect to t on both sides. Okay, what is the derivative of tangent? Well, that is secant square, right? And d theta dt. What is the derivative of y? 1, right? But you gotta multiply by dy dt. Okay, now let's see. After 30 seconds, what happened after 30 seconds? So it was like the hot air balloon rise vertically. Okay, so after 30 seconds, what happened? Will the 200 change? No, the 200 stay the same. But after 30 seconds, what happened? What is the y? The y is 4 meter per second times 30 seconds is 120. So this is 120. So if we know this triangle, this is 120, this is 200, and what is the other side? So we have square root of 120 squared plus 200 squared. Okay, what do we get? So let's see. Okay, so square root. Yeah, you can help me to type it together. 120 squared plus 200 squared is actually not a whole number. Okay, so let's see. Okay, so this guy, because it's not a whole number, so let's keep it like this first. And then we plug in at the end to make our answer more accurate. So don't keep the decimal here. So let's put exact number here. We calculate at the very end, and then our answer will be more accurate. Okay, so what are we looking for? We are looking for d theta dt. So here dy dt, we know that is 4. But what is secant? Well, secant is what? Secant theta is 1 over cosine, right? Cosine is adjacent over hypotenuse. Then secant is hypotenuse over adjacent. So this guy is hypotenuse squared, which is 54400 over adjacent square. D theta dt equals 1 over 200 times 4. Then d theta dt equals to, let's see. So here we can see the one copy of the 200 cancel. And then 4 times 200 over 54400. Okay, let me plug this in my calculator. Okay, so the answer is approximately 0.014706. Okay, what is the unit? Okay, this is radian per second. Okay, do you have the same answer? All right, good. Okay, so okay, so let's continue to the next video.